Good morning. I will talk about geometric uncertainties, errors and uncertainties in Linac and CyberKnife SRS SBRT. You might think, what's she talking about? 1 millimeter, let's go home. The goal of my presentation is really to make you realize that things may not be as easy as you think, and it's actually wonderful complexity in there. Let's talk about the organization of my presentation first. I'll first define what we're talking about, accuracy of language. I will then as I go through my slides, introduce the specific uncertainty I'm talking about, give you an example on the Linac, because that's what we're most familiar with, and also give you an example on the CyberKnife to compare and contrast. So, language. A lot of these words, like errors and uncertainties, we use in our colloquial language. But when you use them in science, they have a very specific meaning. And just to emphasize that, I wanted to repeat. The error is the result of the measurement, here's my mouse, measurement, minus the true value of the measurand. This is the ground truth that we do know nothing about, and this is our result. The uncertainty is a parameter which is associated with the result of a measurement that characterizes the dispersion of the values that could reasonably be attributed to the measurement. We often assume that the dispersion of values follows a bell-shaped curve, and we often use as uncertainty the value of sigma of these bell-shaped curves. But these uncertainties may have other shaped distributions. We should be aware of that and not just automatically think about the default. Accuracy and precision are another two words that are often confused in colloquial language. Accuracy is the closeness of the agreement between the result of a measurement and the true value of the measurand, a low error. So, precision, on the other hand, is the closeness of agreement between independent test results obtained under stipulated conditions. I always explain this with when you go to the shooting range, your goal is to be both accurate and precise, obviously. Most people are somewhat accurate in that their distribution of their measurands or their shots is somewhat around the middle of the target, but is somewhat imprecise. If your sight is misaligned and you are a good shot, you can have still a very precise result, but you're obviously going to be very inaccurate. And if you're out in the shooting range for the first time, you're going to be both inaccurate and imprecise. And I use that always to remember what these words mean, especially this plot. To drive it home again, I couldn't find a higher resolution. Despite much practice, Ernest here is very precisely hitting the door, but he's not very accurate. Repeatability and reproducibility are also two very closely related but different meanings. Repeatability is the closeness of the measurement when measured under identical conditions. For example, if I go measure an output factor with the blue water tank and the edge diode on CyberKnife 2, the closeness of those measurements are the repeatability. Reproducibility is the closeness of measurements when measured under changing conditions. Indrin showed this wonderful plot of the 6 by 6 millimeter output factor for different devices, different people. The reproducibility of that measurement clearly was low. So this was an output factor measured by different physicists at different locations using one of many diodes out there in a water tank. Both relate to precision, but they're not identical to precision. And I'm hoping that throughout the lecture I will use these words correctly. It's actually harder than you think. So enough with the definition. Let's go measure something. If you think about our major contributors to uncertainty, we have mechanical errors that I will focus on, dosimetric errors that Indrin discussed in detail, and some treatment errors. And this is more a summary slide for your own reference. I won't go in detail very much here. Let's talk about mechanical accuracy mostly in this lecture. We've all done this. If you want to check the Linac Mechanical Radiation Isocenters, we go in and we do our star shots. We do segmentation of our results, calculate the smallest intersecting circle, and the radius of that smallest intersecting circle we call the radiation isocenter size. Very straightforward. Although a lot of residents don't understand the smallest intersecting circle, so remember that. If you look at TG142, it gives you the mechanical tolerance limits that you should be able to achieve with SRS and SBRT, and pretty much most modern machines can do this very easily. But when you look at these and think about it, these are actually all independent errors. And independent type A errors we're supposed to add in quadrature. If all of these are close to 1 millimeter and you add them in quadrature, your mechanical uncertainty is well above 1 millimeter. Let's hold that thought for later. The CyberKnife, contrary to common belief, does have a mechanical isocenter. It's just not as easily visible. We have a thing called an isopost, and if you go into a CyberKnife room and you look into a corner, you usually find it hanging out there. And on top of the isopost is a tiny, about a 1 millimeter diameter, what they call an isocrystal. It's a optical detector. And what you do, and that actually defines the mechanical isocenter of the room and is also the origin of different coordinate systems. The robot coordinate system, which is rotated 45 degrees to the patient coordinate system. There's a imaging coordinate system, which I haven't drawn in this picture, and the synchrony coordinate system. And the tip of the isocrystal defines the origin of this coordinate systems and is the mechanical isocenter. To do a calibration of the robot to isocenter, we obviously don't do star shots, but we go for every node and run a grid pattern over this isocrystal and measure at which position there is the highest light intensity. And what you get as a result of that, after you've run your grid pattern, you get this, for each robot node that was originally installed, you get this correction vector that points you in which direction you need to shift that node to point the laser to the isocrystal. After you've run this calibration and employed all these green correction factors, you run this whole thing again with a verification. And from the verification, you get this table. For example, at point 1, this is the original coordinate system. This is the calibrated node. The difference is obviously this vector. Then you run the verification. You get an error compared to this node. You add this error in quadrature. You get the error of each node by the verification. And then you add all these errors for one path in quadrature, and the acceptance says you should be less than 0.5 millimeter average root mean square error per path. In reality, if you have a new machine, one of the modern robots, you're usually sitting around 0.2, 0.3 millimeters. It's a very precise and accurate machine. So, and we know that the robot pointing is actually stable for up to 2 years. We don't have longer data because people tend to upgrade and make changes and recalibrate. So, once you have your mechanical isocenter, we are image guided now, and we now need to match the imaging isocenter. This is a very nice paper by Michael Sharp that you actually should read. So what we've done so far, we have some MV radiation isocenter. It's related to the nominal isocenter, and we have an MV mechanical isocenter, and we've matched these very closely with our star shots. Now you put a phantom with a BB on the couch using the lasers, and there's your KV imaging isocenter somewhere. You do an MV image, and you shift these BBs into this MV isocenter here. And then you run your imaging calibration, which tells you what the vector is between the KV mechanical isocenter to the MV isocenter, and you make that shift. CyberKnife is actually a little bit easier because we don't have these two arms coming out and rotating in a cone beam CT. We have these two imagers that are very solidly bolted into the room floor and the 2 cameras bolted into the ceiling. And to tell you how solid they are, I've been with the system through a 5.3 earthquake in California, and they didn't move at all. So, very solid. And the imaging system is calibrated simply by taking well, the original calibration is more complex, but once the engineers have set it up, you take an image of the isocrystal, of the isopost, and you see the isocrystal very faint here. And you can then check with the cross-section of your imager if the isocrystal is actually centered here. The centering tolerance is 1 millimeter or 2 pixel sizes. And as I said, it's a very stable and very simplistic system. There is a beauty to simplicity. Now, when we used to have cones, everything was easier. Now with the 2.5 millimeter leaves, and we're doing MLC-based stereotactic radiosurgery, we need to also worry about the MLC accuracy. The first thing you notice, if you look at TG142, it gives you the tolerance level of segmental and moving window IMRT. And that's about 3.5 millimeters. How does that relate to the 1 millimeter accuracy of stereotactic radiosurgery delivery? Interestingly enough, also, if you look at leaf position accuracy, they give you 1 millimeter for leaf position. So, for the 40 cardinal gantry angles in a picket fence test. So, in clinical practice, I would hope that these numbers are actually more closely related to these numbers. I'm not sure where they got these from. But still, that's just for your leaf position in addition to the mechanical uncertainties of 1 millimeter for each of the rotational axes of a Linac. Let's hold that thought. CyberKnife, as I said, used to be easy with the fixed collimators. We didn't have to think about uncertainties like that. What you commission in your data reflects the actual mechanical collimator, nothing changes. With the IRIS Collimator, it's a little bit more different. The aperture reproducibility at the lower leaf bank, which sits at 40 centimeter SAD, is plus minus 1 millimeter. And the root mean square variation in the 50% dose radius is less than 0.8%. The root mean square variation in the 20 to 80% penumbra is 0.1 millimeter for the 5 millimeter cone and can range up to 0.5 millimeter for the 60 millimeter cone. So what you need to think about now, both that the mechanical uncertainty has some impact on your commissioning data, and when you do beam data measurements, you need to be very careful to follow the established protocols to make sure that your beam data reflects your most likely size of the iris. Because 0.1 millimeter doesn't sound like much if you think about a 1 millimeter MLC leaf uncertainty that TG142 defines. But if you're talking about 5 millimeter collimators, that's actually a pretty sizable change in the opening. And coming back to what Indran says, this is a sizable change in occlusion of your source size. So if you look at measure the iris opening with a camera, and you look at the commissioned full width half maximum effective beam diameter in a face-to-face method, somehow I have same formatting issues as Indran. You can see that there is a mean difference from the nominal, which is okay because your beam data will reflect that, but there's also some uncertainty associated with that. And you should be aware of the size of these error bars. So next up, we're testing the imaging algorithm. And this time I flipped it. I start with the CyberKnife first because it's the easiest. If you set up the patient on the table, we have another part of uncertainty coming in. We now not just setting up a patient in a frame anymore. If you go frameless, you're using an algorithm to compare your patient position to the CT. And when you do CyberKnife commissioning, you actually see one of the, what I think, most beautiful and elegant ways of QAing that imaging algorithm, which is you taking an anthropomorphic phantom and mounting that on the tip of your robot, and you've already tested with the path alignment that your robot is an extremely accurate machine, 0.2 to 0.3 millimeters. And then you're running this phantom through different translations and rotations, and you're going to take a look at what the result of the imager, what the imager tells you how much the phantom has shifted compared to what you have told the robot. And you can see overall that the imaging algorithm gives you a very, very accurate result. And both in translations and rotations. This is a wonderful test. And it's probably one of the most underutilized tests, I believe, in the area of image-guided stereotactic radiosurgery. How often do we check the performance of our image guidance algorithms, not on BBs, but something that's realistic and more close to the patient? So the first question is, what is the tolerance of the CyberKnife Isocrystal to Isocenter? 0.5 millimeter, 2 millimeter, 1 pixel, or 2 pixels? Okay, it's actually 1 millimeter, which is about 2 pixels, but not quite the same. 0.5 millimeter is too small. So the image of the isocrystal should be within 1 millimeter of the isocenter. And as a reference, you have AAPM TG135 as well as the CyberKnife User's Guide. Now we've talked about all these individual areas, mechanical, imagers, tracking algorithms. How do these combine? And there's a test that we also should use more, the end-to-end or delta, also used for delta man. The end-to-end test is actually a variation of the old Winston-Lutz test, which was good when we did frame-based stereotactic radiosurgery with cones and arcs. We're not doing that anymore, so we need to upgrade our QA as well. For the end-to-end, you're going to use an anthropomorphic phantom with some kind of hidden target. This is a very round, nice artificial brain mat, and you have some kind of detector. I prefer film for the resolution. And you're going to deliver a dose distribution. And what you're going to do is you're going to deliver an isocentric plan in a relatively homogeneous phantom. Yes, you have bone, but the rest is pretty homogeneous. And then you measure the shift of the delivered 70% isodose line versus your plan. This was one of the best end-to-ends I ever did. That's why I keep showing it. And the tolerance, and that's what you actually hear when you hear that the CyberKnife achieves accuracy of less than 1 millimeter. They're actually referring to the end-to-end test, to the comparison of the 70% isodose line versus the plan, and the center of this isodose line is within 1 millimeter of the planned dose. So you can do the same exercise on the TrueBeam, which Lei Wang actually did. Same thing, you run the films, you do the isodose lines, you can do a gamma analysis. And what you actually find if you go through this exercise with both flattening filter-free and flattened beams with IMRT and with rapid arc, get a wonderful table. And the magnitude of your end-to-end test ranges from of that uncertainty of delivered dose versus planned dose from 0.4 to 0.85 millimeters, which is pretty much what you get with a CyberKnife. A well-calibrated CyberKnife runs between 0.6 and 0.8 millimeters. So if you use that test, those two machines perform the same, even though they have very different origins of mechanical uncertainties, very different ways these mechanical uncertainties combine. I should note, though, that this result on the TrueBeam is a FYI. You know what it is. You don't perform any mechanical correction in action. On the CyberKnife, however, there is this little magic that happens that's called the delta man. This is actually not true anymore. You don't run the end-to-end for all tracking algorithms anymore, but you run it for fixed beam and IRIS. You could do this, and it's a good exercise to do it, because it tells you about the difference between algorithms, but per commissioning instructions, you don't do it anymore. So you run your end-to-end test a couple times, and you can, from that result, then determine a systematic translational shift. And then you can apply this result as a global correction. And the reason why you do this is if you think about how you did your mechanical isocenter alignment, you did that with the beam laser. You didn't do that with the actual beam. Now the beam laser to beam has an uncertainty. And it's not as easy as measuring, putting a film in, measuring where the highest and where the cax of your beam is, looking where your laser is making the shift, because your CyberKnife rotates in all different directions. So the way the beam and the Linac combine and shift is different. So what you do then is just use this delta man as the overall fudge factor to look at the average systematic uncertainty that's created by this uncertainty between the Linac and the beam central axis. And you apply this as a global correction, both for fixed and IRIS. And then you repeat this exercise, you do your end-to-end, you shift your delta man until you're nominally under 0.95 millimeter, and in practicality it's more like 0.6 millimeter. So, repetition. Yeah. Let me just talk also about some uncertainties common to all stereotactic radiosurgery systems. And how far am I in time? I don't have a timer here. Indrin talked about dosimetric accuracy, and I'll keep it very short. I just wanted to remind you of the highlights of his lecture. Dose calculation uncertainty translates in spatially shifting isodose lines. Indrin has shown this for long. I just want to drive this home. This shows up in unexpected areas. Here, for example, in the spine. I have a vertebral body here that abuts the lung. And if you see a pencil beam algorithm here versus a Monte Carlo, because I have beam contributions from this side, there is about a 1 millimeter shift in the position of isodose line. So when you do stereotactic body radiation therapy, don't neglect and brush under the carpet your dosimetric uncertainty. This is actually translates in positional uncertainty of your isodose line. And you need to take that into account. Commissioning beam data, all cones come with error bars. TG106 states that the inter-user and equipment repeatability should be less than 1%. If you look at Indrin's plot that he showed, we as a community are not there yet. We are on the learning curve of getting our repeatability, of measuring these output factors to this 1% recommendation. If you're measuring, for example, CyberKnife, you need 3 or 4 sets of data, output factor, TPR, and profiles, and you put this in your planning system, and to be honest, I haven't solved the problem yet how to combine these different uncertainties in everything and say this is the uncertainty in my beam data and this is the uncertainty it causes in the position of the isodose line. The assumption is that you can get to a 1% error each for unconnected data sets. I find that a little bit on the optimistic side, to be honest. And to repeat again, I do not know how to express just the fact that we're taking beam data and we have repeatability and reproducibility errors and translate this as a spatial uncertainty. I think there's a rich opportunity here for some research. I'll skip that because Indrin talked about it. Residual patient motion. This is also uncertainty. Geometric uncertainty we need to think about if we're not in a frame. So if you just look at how a patient moves over time, you can see for cranial radiosurgery in a mask, you can see this slow systematic shift. And the more complex your plan and the longer your delivery, the more you drift away from your original image, or the longer you wait between taking the cone beam and the physician actually showing up to approve the cone beam. Don't forget about that time. If you don't correct for that, if you just take an image at the beginning and your mean offset can actually exceed 1 millimeter easily. So what that tells you is if your treatment times or the time between imaging and start of treatment exceeds, let's say 5 minutes, you need to start worrying about this difference in spatial shift from the patient movement. This is an older CyberKnife paper, but what I liked is they took all these data points and looked at the residual error and looked at if you don't correct for intrafraction patient motion, you can actually have a very large uncertainty, combined uncertainty, if you assume that von Herk does hold. And if you correct for that, you're actually getting lower, but still above 1 millimeter. And this is just residual motion between images and not residual motion overall. So this is actually makes the case that you need intrafraction motion monitoring if your fraction length is anything more than 5 minutes. The results depends on your imaging frequency and treatment delivery time. This is older data. The errors are more likely much smaller now. So let's take a step back and summarize what we've learned so far. We've looked at qualitative accuracy comparison of stereotactic radiosurgery with Linac and CyberKnife. We found actually mechanically commissioning data, patient positioning uncertainty, target localization, dose calculation algorithms. They're all pretty similar errors if you add everything up. But it's actually quite hard to make this comparison. While the Linac stereotactic radiosurgery accuracy contributing factors are generally similar on the same order of magnitude as the CyberKnife, they do combine differently. Why is that? You have the delta man concept on the CyberKnife to determine and adjust systematic and mechanical imaging errors. We don't usually do this exercise on a Linac, and what's the word I'm fishing for here? I'm arguing for that we actually should start doing this, like Lei Wang did, standard on the Linac, because it is such a nice overall test of how all your uncertainties combine. And it gives you an idea how accurately you can actually deliver a brain met dose. There's intrafraction imaging and positioning correction, which is clinical on the CyberKnife, under development on the Linac, where there are centers which are very far ahead that have intrabeam imaging, either optical, like UC San Diego, Laura Cervino does, or they do other intrabeam imaging. But there's a wider spread of clinical practice on a Linac. And we have very different treatment times, so that also factors in. Linac treatment times for stereotactic radiosurgery can range from a single arc that's done in 2 minutes to a complicated IMRT delivery that takes, with breath hold, that takes half an hour or more. So you also have a wide range here. So my dream here is, and we're not there yet, but I think we as a community need to go there, is that we need to measure these uncertainties, mechanical, dosimetric, overall uncertainties, with the same or as similar as possible test procedures on all 3 modalities. And with that I mean CyberKnife, Gamma Knife, Steve Gertsch is here, our Linacs, tomotherapy. You can also do stereotactic radiosurgery in whatever other machine you have. Because right now, if someone tells you, oh, my machine has X amount of uncertainty for stereotactic radiosurgery, we're not just comparing apples to oranges, we're comparing apples to potatoes. So you need to be very careful and ask, what do you define as your uncertainty? There's other treatment uncertainties. Imaging and registration I've talked about. We're still using CTs and MRIs for planning. And if you look at comparison of measured target positions with mechanically known coordinates, we all know that the highest accuracy, as we expect, is from CT, and MRI is more susceptible to distortions. As we're doing more image fusion, we have ViewRay and other things, and MR can be a very good tool to contour, treat, and even plan. But we need to pay attention that this MRI is well shimmed, well maintained to not have distortion. And I've seen distortions of up to 2 millimeters over the range of a cranial MRI at a very well-known institution on the West Coast. So think about that if you use MRI, and ideally we usually don't know how radiology QAs their MRIs. We often do not know in larger institutions who the physicists are. My recommendation is go seek that physicist out and invite him or her to lunch and have a talk about this, because you need to know this. Image fusion, there is an upcoming task group led by Christy Brock. We used to do rigid registration in the brain, and that's very, very accurate. You can see numbers of 0.2 to 0.4 millimeters. We can do fusions performed in dedicated planning systems or with third-party systems. We have mutual information-based algorithms, but the accuracy depends on amount of the common data we use, the voxel size of the images used, and what the actual accuracy of your fusion is, it really determines on your both your imaging protocol that you at your institution are using and what combination of software we're using. And I think this is one of the big dangers right now. We are throwing 2 images in there, we let the algorithm fuse, we're checking a few parts of visible anatomy, but not everything, because soft tissue is hard to check at times. MRI versus CT, you don't have clear landmarks. And then we trust what's on the screen there. And before you really do that, you need to look at some papers that are actually stating, especially if you go to body, if you move outside the brain, these errors of the image and uncertainties of the image fusion algorithms can be 5 millimeters and above. And you need to really, really carefully assess that. And once the task group 132, comes out, take a very close look at that before you use image fusion for contouring in SRS. Just to repeat, which imaging modality has the highest spatial localization accuracy in a phantom? CT, PET, SPECT, MRI, or ultrasound? CT, yes, is our gold standard, and second most accurate is MRI, but even if it's a very well-maintained MRI machine, it usually cannot reach quite the accuracy of CT. So, at the very last, so we have poured tremendous effort as physicists to measure, study our uncertainties, both mechanical, both dosimetric. We have a getting grip on how these combine, what the overall uncertainty is. And then there's the elephant in the room. It's more like a herd of elephants. I just want to talk about this, just to put, you might be scared by all these uncertainties, but let's be realistic. The famous expert user papers. Ex-experts, users are given the same patient to contour, and this paper I'm giving here is an example of an AVM. Same thing in all papers here. The agreement ratio is just dismal. And honestly, an AVM is not that difficult. There are other brain tumors which are way harder to contour. Agreement ratio between different expert users is less than 60%. We need to encourage our physician colleagues to do something about this. This is, I don't know. It gets me a little bit aggravated. 50% of the time, the absolute positional shift of the center of mass of your target here is larger than 2 millimeters. This is a well-visualized AVM. Okay. Another thing that I hadn't thought about before I found this paper here also, your higher accuracy of delivery, all this effort we as physicists have poured in the last 10 years, actually means that we have now way less room for uncertainty. If you look at this image, this is again this contour of one of the AVMs. This is image A is planned for isocentric with one cone. B is isocentric. No, this is actually also one cone, just from a different angle. C is a dynamic conformal arc plan. And if you look at coverage of all the contours here, because you treat so much normal tissue with a one cone necessarily, because you have an irregularly shaped target, but you have a round cone, you have a nice safety margin. If you plan to to the average contour here, and then you take the combined contour, you're only covering about 80% of the maximum combined contour of your MIP, so to say. So in the face of anatomical contouring uncertainty, we have now a much smaller safety margins than before relative to physician uncertainty of target localization. And I've just thrown in a few more references on the topic to do a more closer lesion. There are concerns regarding accuracy. We're relatively safe still with brain metastases because they tend to be round. We are still not, we're still in the dose gradient, so even if there's a little bit uncertainty in the contouring, you're still going to cover most of the target. And just as a side note, if you have one of these anthropomorphic head phantoms from a CyberKnife or otherwise lying around, and you have this hidden target, take a CT and make your resident or your physician, if they're up for it, contour that well-known target where you know the volume. And I promise my residents a bar of chocolate for the resident who comes closest to the actual volume. And you will learn something very, very interesting about visual perception of what a target size is on a grayscale CT image. I can tell you that most physicians get a significantly larger volume. It's usually between 10 to 20% larger than the actual volume of that plastic ball. Do that exercise, or do that exercise yourself. It's excellent learning. We have some tools that can help us. Autosegmentation is the keyword here. This is a very interesting paper that looked at let physicians contour de novo these cases, like the standard expert users papers, and then they threw in a little kick, and I thought this was quite ingenious. They had their software auto-contour anatomical targets based on a contouring atlas, and then they told physicians to modify the contour as they saw fit. And what was actually amazing is that if physicians started out with already segmented contours and edited those contours still based on their clinical judgments, their contours agreed much better with each other than they did if the physicians just started with a blank slate. So this is an area we actually, I think, need to explore more to improve our accuracy in stereotactic radiosurgery. Just to go back on that paper, what effect will higher technical targeting accuracy have on the required target contouring accuracy? They're not related. CTV margin can be reduced. A fused image set should be used. A contouring atlas must be used, or it leaves less room for contouring uncertainty. Yes, most of you got it. It's a slightly challenging question to ask, but if the CTV margin depends on the extent of the microscopic disease, that does not change. This is a clinical or pathology question. A higher technical accuracy means that there's more conformality to the tumor contour in your treatment plan. Therefore, if you have very tight coverage, especially of an irregular lesion, you have less room for contouring uncertainties. Using a contouring atlas may help in accurately contouring organs at risk, but it's not a must. So you can go back to slide, I think, number 41. So in conclusion, and I hope I'm still in time, dedicated radiosurgery machines can deliver dose very accurately to homogeneous phantoms. Treatment planning systems are getting much more accurate. When I started out, most of RTOG still just required pencil beam. So in vivo studies of dose calculation accuracy or anthropomorphic phantom DQA is pretty sparse in SRS or SBRT. We have lots of comparisons of Monte Carlo versus other treatment planning algorithms. We're starting to see more film-based papers, as Indran has shown, but it's still relatively sparse, and it's mostly targeted at lung and not at other targets like spine, where we also have large inhomogeneities. Delivery quality assurance methods that we currently have, we have technical limits measuring to an accuracy better than 3% in 1 millimeter. 3% 1 millimeter is pretty much film QA. What we haven't gotten a good grip about, and I haven't even talked about that, but we should keep that in the back of our minds. We have still uncertainties in radiation biology. We still have large uncertainties in imaging where the disease actually is, and that ties back into that contouring uncertainty. So there is actually, I think that's the largest area of improvement to reduce uncertainties. We still have large uncertainties in image registration, especially if we go to deformable registration in the body for SBRT. And all these, the radiation biology, imaging the disease, and image registration and contouring are now large uncertainties compared to where we as physicists gotten to our mechanical and dosimetric uncertainty. So we've done our jobs here in the last 15 years, and now it's time to focus on our attention here to get more accurate and precise. And with that, I'll close. Thank you.